Hello, everyone. Welcome to the second lecture of our course on heterogeneous systems. Today, we are going to continue talking about SIMD processors, and we are going to start introducing the programming model and the architecture of GPUs. Remember, we saw this slide the other day as an example of what can be a heterogeneous computing system these days. Here we can identify CPU cores, GPU cores, and also reconfigurable fabrics. There might be other accelerators, like, for example, neural network accelerators. And this is just an example, heterogeneous computing system. Remember that these computing devices are somehow or can be somehow classified following Flynn's taxonomy of computers. Remember that there are like 4 main classes: SIMD, single instruction operates on a single data element. The best example is a sequential processor. We have SIMD, where single instruction operates on multiple data elements. And today we are going to talk with a little bit of detail about two, let's say, paradigms in SIMD processing: array processors and vector processors. Then we have MISTY, when multiple instructions operate on a single data element. And finally, we have MIMD. Multiple instructions operate on multiple data elements. We have multiple instruction streams, as we typically have in multiprocessors or multi-thread processors. Today, we're also going to talk about MIMD, but let's first start with SIMD processors. The basic idea in SIMD processing is to exploit data parallelism. In data parallelism, concurrency arises from performing the same operation on different pieces of data. That's why we call it single instruction multiple data. A good example of this computing paradigm is the way that we can execute the vector product, the dot product of two vectors, where we have multiple operations, for example, multiplications that can be executing in parallel. And after the multiplications, we can perform a reduction to obtain the result of the dot product. This type of parallelism is different from the type of parallelism that we can extract in data flow computers, for example, where concurrency arises from executing different operations in parallel in a data-driven manner. Or the SIMD paradigm also contrasts with thread or control parallelism, where concurrency arises from executing different threads of control in parallel. In the end, SIMD exploits operation level parallelism on different data. We have the same operation concurrently applied to different pieces of data. And this, if you think about it, is kind of a form of instruction level parallelism. But in this case, the instruction happens to be the same across all the data elements that we operate on. So in SIMD processing, a single instruction operates on multiple data elements, and this might happen in time or in space. We assume that we have multiple processing elements, execution units, and we can use them either in time or in space. And this is what we call the time-space duality, that essentially determines what the difference is between an array processor, where one instruction operates on multiple data elements at the same time using different spaces, and a vector processor, where one instruction operates on multiple data elements in consecutive time steps using the same space. We are going to see a clear example with this toy representation of an array processor and a vector processor. On the left-hand side, you can see our first vector program or SIMD program composed by 4 instructions: a vector load, vector add, vector multiplication, and vector store operation. Notice that, for example, here in the vector load instruction, we are accessing 4 elements from memory from an array called A. We are access 4 elements at a time and store these 4 elements in a vector register that should be as wide as needed to hold the 4 elements of the array A. Then we perform the addition, multiplication, and finally store the result back to the 4 positions of array A. How is this program executed on an array processor? Well, first of all, in the array processor, we have 4 processing elements that are exactly the same, and they have the ability to execute different instructions. So in the very first cycle of the execution of this instruction stream, we can launch 4 loads, 1 in each processing element. After that, after the load operation is complete and we have the data, the elements from A in the vector register, we can execute the add instruction, then the multiply instruction, and finally the store instruction. However, in the vector processor, what we have is also 4 processing elements, but in this case, each processing element is specialized on a specific operation: load, add, mul, and store. So in the very first cycle, we can only start executing one of the instances of the vector load. It's a load word 0 or element 0. In the next cycle, we start the execution, or not exactly in the next cycle, probably after the load of the first element, element 0 finishes, we can start the execution of the next element, element 1. And at the same time, in the add unit, we can start the addition with the element that A0 that we just got from memory. And we can continue in next cycles, or after each of these instructions finish, we can continue with the execution and complete the program using the 4 different units that we have in the vector processor. So as you can see, in the array processor, we have the same operation at the same time, while in the vector processor, we have different operations being executed on the existing units at the same time. And in space, in the array processor, we have different operations in the same space because these processing elements are able to execute different instructions, while in the vector processor, we have the same operation in the same space. So now let's start thinking about how we really execute code on the vector or array processor, because in the end, even though the let's say the specific hardware of them might be different, but the abstract representation that they have and the way that we execute the programs from an abstract point of view is exactly the same. So that's why we are going to focus on vector processors. So let's start considering, defining what's a vector. A vector is a one-dimensional array of numbers, and many programs, many applications use vectors, as you know. We have very naive, simple code for a start. Here is a for loop that goes over 50 elements of arrays A, B, and C. And what it's doing is reading elements from arrays A and B from memory, adding these elements with the same index, dividing the intermediate result by 2, and storing the result in array C, in the corresponding element of array C. So in a vector processor, we have instructions, we have vector instructions that operate on vectors rather than scalars. If you look at the code that we have on the slide, we have 2 vectors and we are operating on the vectors. The only problem with this code, with this simple code, is that we are operating on these 2 vectors sequentially. But the fact that we have to apply exactly the same computation on all the elements of A, B, and C allows us to use a single instruction to execute all these operations at the same time on these 50 elements that we have in these arrays. But we need some basic requirements for vector processor. First of all, we need to load and store vectors, and we have to have the ability to store the data that we read from memory in some registers that are closer to the execution units, and these are the vector registers. We need to operate on vectors of different length because this for loop has 50 iterations, but other for loops will have a different number of iterations, and we can play with the vector length register here. And also, we need to have a way of accessing memory. In the particular case of this code, all the accesses are consecutive. So all elements accessed from arrays A, B, and C are consecutive. So the stride between this element is just 1, but it's not going to be the case for all workloads. So that's why we need to have a vector stride register that tells us what's the distance between consecutive accesses in memory of a vector in order to calculate the addresses that we have to access in memory. As an example of this, we have a matrix multiplication. In matrix multiplication, we have 2 input matrices, A and B. We assume that both are stored in memory in row major order. And as you know, the way of multiplying matrices A and B is by performing the dot product of 1 row from A and 1 column from B. So let's assume, because memory is linear, or memory addressing is linear, we know that arrays A and B can be stored in memory in a layout like this. So if we have to compute elements of C, as I said before, we have to calculate the dot product between one row of matrix A and one column of matrix B. The way that we access matrix A is by using a stride of 1, because all the elements that belong to the same row are consecutive in memory. So the stride between elements 0, 1, 2, 3, 4 is only 1, as you can see in memory. So in this case, every time that we are going to access with our load unit one of these elements in memory, we have to increment the address by 1 to access the next column, the next element in the row. So the stride here is 1. However, when we access matrix B or the columns of matrix B, notice that elements in the same column are at a certain distance in memory, as you can see in the slide. In this case, this distance is 10. So the stride is 10 in this case. We will talk again about what are the considerations to be taken into account when we are using strides. So now, in a vector instruction performs an operation on each data element in consecutive cycles. So vector functional units are pipeline. In the most basic example of a vector processor, we are going to assume that we have only one single functional unit for each instruction, as in the simplified vector processor that we saw a couple of slides ago. But these units are pipelines. So in each pipeline stage, we are operating on a different data element of the vector. The good thing is that because we are going to use vector processors typically to execute long loops, for loops, for example, as in the code as we just discussed in the previous slide, this allows us to have wide vector lengths and allow deeper pipelines. And this has certain advantages because there are no intra-vector dependencies, so there is no hardware interlocking needed within a vector. There is no control flow within a vector because all the elements, we perform the same operation, exactly the same instruction on all the elements of the vector. There is a known stride to easily calculate the address for the accesses, loads and stores between memory and the vector registers, as we have just seen in the previous example with the matrix multiplication. And this allows to do easy loading and even do prefetching because we know what are going to be the next elements to be accessed. We can calculate those addresses in advance because we know the stride, and we could be prefetching some data from memory and hide latency in this way. But doing all of that has the difficulty that programming is difficult. And this is something that we already discussed in the previous lecture. And also it's a motivation for this course where we are going to cover with a lot of depth how to program GPUs, which are representative SIMD processors these days, as we are going to discuss, or we are going to continue discussing in this lecture. Regarding the vector registers, we are going to assume that each vector data register can hold n bit values. So here you have at the bottom of the slides some simplified representations of vector registers. So this could be vector 0, and vector 0, as you observe, can contain n elements, and each of these elements has m bytes. We also have the vector control registers that we have already mentioned, at least a couple of them before. The vector length that defines what's the length of the vector that we are operating on, or the part of the vector, a longer vector that we are operating on, the vector stride to calculate the access, and then we have a vector mask. And that's going to be very useful to execute for conditional execution. For example, implement if-else statements in vector and SIMD processors. There is a maximum vector length that can be n. In the end is the maximum number of elements that you can store in the vector register. And then, as I said, the vector mask indicates, or the vector mask register indicates which elements of the vector we have to operate on. For example, imagine a code where we have an if statement to check if an index is even or odd. Depending on that, we are going to perform one operation or a different operation. That's the conditional execution that I meant. Now, in order to fill these vectors with data, we have to access memory. And after computing, we also have to write back to memory, right? So we have to figure out a way of loading and storing multiple elements at the same time or in consecutive cycles. We know that these elements might be at a certain distance that we call the stride. For now, we are going to assume a stride equal 1. We want to access elements of the vector from memory either at the same time, if that's possible, or in consecutive cycles. So for now, we are going to assume that we need to wait a certain number of cycles, a latency, to access each element from memory, but we want to sustain a throughput of one element per cycle. That's going to be the bandwidth of our memory. But how can we do that if the latency takes longer than one cycle? The way of doing this is creating not a monolithic memory, but a banked or interleaved memory. In a banked memory, what we normally have is the memory divided into different parts called banks. And all these different parts can be accessed simultaneously. So the memory is divided into banks that can be accessed independently and simultaneously, depending on what are the addresses and databases, that we have. And we are, for now, going to assume that we can start one bank access per cycle. So, but we are going to be able to sustain n concurrent accesses if they go to n different banks. So observe that for each of these banks, we have a memory address register and we have a memory data register. Using the address bus, we place here in the memory address register the address that we want to access from each bank, in this case from bank 0 or bank 1. And after a number of cycles, after the latency, the memory latency, we will have here in the memory data register the value that we want to retrieve. It's exactly the same, but the other way around, in the opposite direction, if we want to perform a write operation. The only point here is that from this address bus, we are able to place the address in one of these MAR in one cycle. So what that means is that we start the accesses to different banks in consecutive cycles. Okay, let's continue talking about, we will go back to the memory, but let's continue talking about the vectorizable loops and this code, that simple code, this simple for loop that we saw a couple of slides ago. Loop is vectorizable if each iteration is independent of another iteration. That's the case in this code indeed. As you see, we go from element 0 to element 49, but the operation that we perform using element AI, BI, and CI is completely independent for each I. What that means is that we can operate, so we can vectorize this loop. What that means is that we can operate on all these iterations in parallel using a vector processor. And that this is the way, or this is how this vectorized loop can look. First of all, we have to set what's the vector length. In this case is 50, that is the number of iterations in the for loop. Imagine that this number was much higher, much longer, and this 50 was the maximum vector length that we could have, the n that we had in the previous slide. Well, what that means is that we would need to operate on first 50 elements, then another 50 elements, and so on. In this case, also, the vector stride register is set to 1 because we access all elements of arrays A, B, and C. And then here at this point, with this vector load, let's say the vectorized code starts. First of all, we have the load instruction for, to array A. Then we load array elements from array B. Then we add the elements that we have previously loaded in vector 0 and vector 1. In the next instruction, we shift right. Remember that right shifting is the same as dividing by 2. And finally, we store the result in array C. Observe that here at the right-hand side, we have the latencies of each instruction. For now, we assume that these move I instructions just take one cycle. But then, for example, the load instructions are going to take longer. Typically, memory accesses are operations with longer latencies. In our example, we assume that one individual access to one bank in our memory is going to take 11 cycles. But observe that because we are going to use a bank memory, we are going to be able to issue a new load to a different bank every cycle. And what that means is that after 11 cycles, we have retrieved element A0. One cycle later, we have retrieved element A1, and one cycle later, element A2, and so on. And it's the same for the other execution units, like for example, for another. For example, the latency in this other is 4 cycles, but because the other is going to be pipeline, one cycle later, we will have the addition for the next element of the vector. And same for other execution units like multipliers or the ALU that executes this shift right operation. In total, as you see, we have 7 dynamic instructions. So for now, we are going to assume that there is no chaining. Chaining means vector data forwarding. We are going to define it better in the next slide. Well, here is the definition. The output of the vector functional unit cannot be used as the direct input of another. What that means is that for now, we cannot forward the output of the load unit, the first element of that we get with the load unit, we cannot forward it to the add unit. So what that means is that we cannot start the execution of the add instruction until the load instruction has finished. We are going to see it with a timeline at the bottom of this slide. So the entire vector register needs to be ready before we start a new instruction. And for now, we also assume that there is only one memory port, one address generator. What that means is that we have to wait one cycle to generate the next address to access from memory. And our memory is, we assume that it's an interleaved, a bank memory with 16 memory banks. So because it has 16 memory banks, it's possible to hide the 11 cycles that is a typical latency of access to our memory. And observe that this is the time. And first of all, the 2 move I instructions. At this point here in this cycle, we start the execution of the load instruction. We first need to wait 11 cycles until we get element A0 from bank 0, and then we will start getting one element every cycle from the other banks, element A1, A2, and so on, because we have to read 50 elements that are placed, consecutive elements in consecutive memory banks. We have to wait 49 more cycles to have the complete vector V0. And at that point, we can start the execution of the next load instruction that is executed exactly the same. First of all, wait 11 cycles until we get element B0. After that, we will get one element of B every cycle. After the load instruction, second load instruction is complete, we can execute the addition, perform the operation of the on the 50 elements of vector register 0 and vector register 1. In this case, the latency of the add instruction is 4 cycles. So because this is a pipeline unit, this add unit is a pipeline unit, we have to wait 4 cycles for the first addition to complete, and then we will have the result of the successive additions in the next cycles. And here we have the shift, and finally we have the store operation. So in total, this operation on 50 elements will take 285 cycles. But we want to try to make this more efficient. And there is where we use vector chaining. And what vector chaining essentially means is that we can forward elements or data that has been produced in a specific execution unit or functional unit and move it to another functional unit. So in the particular case of our code, we'll first have to wait for the first load instruction to complete, because we need elements from array B as well to perform the next operation in the next functional unit, that is the addition. So, and remember that we only have a single, for now we only have a single memory port. So we first access array A, we then access array B. But as soon as we have element B0 from, so after these 11 cycles, we can start the execution of the addition in the addition functional unit, as you see here. And after this addition is completed, we have the result of adding A0 and B0. We can shift right that intermediate result, and finally start storing the results into array C. Notice that in this particular case, because we have only one memory port that we use for both loads and stores, we cannot start the store operation until the vector load of array B is completed. But at least we are already optimizing the execution of this code with respect to the previous one in the previous slide. And now we managed to reduce the total execution time to 182 cycles. But still, we can do it better. Why is that? Because these vector loads and vector stores could be pipelined or could happen at the same time. In order to do so, what we are going to assume is that our memory banks don't have a single port, but they can have two load ports and one store port. What that means is that each bank is going to be able to sustain more than one access at a time. And that's how the execution of our vectorizable code would look after incorporating these load and store ports. As soon as we issue the first load, element A0, then we can use the second port to start the access to element B0. So these two accesses to the same banks can happen in parallel. And as soon, because we are using chaining, as soon as element B0 is ready, we can start the execution of the addition, and then continue chaining for the shift register, and finally the store operation. And in this case, we managed to reduce the execution time to 79 cycles. So if you compare to the amount of time that we would need to execute the same code on a sequential machine, you would see a performance improvement of 19 times in this toy example that we are providing. Now, how do we execute conditional operations in a loop? Because the previous vectorizable code was pretty simple, right? We only had to go over all the elements of an array. We could operate on multiple of these elements at the same time, but the operations performed on these elements was exactly the same for all of them. Now we have a relatively more complex code in which we have an if statement, and for every single element of array A, we check if it's 0 or not. And this makes sense because the operation in the body of the if statement is a multiplication. So it makes no sense to multiply elements from array B by 0. But in order to execute this on a SIMD processor, we have to use masked execution. We have to use masked operations. To do so, we have to use the vector mask register, that is a bit mask that determines which data elements we should act upon or we should operate on. So in order to write the vector code for this for loop that we have here, we will need vector load instructions to access elements from arrays A and B. And then we have to calculate we have to check which elements of array A that have been loaded in vector 0, vector register 0, which of them are 0 or different to 0. And based on that, we create a bit mask. And using this bit mask that is stored here in this vector mask, we would execute the next two instructions conditioned or predicated by the values of the bits. This is what we call the predicated execution, because the execution of these two, vector mul and vector store, is predicated on the mask bit. This is very simple example. Here you have a little bit more complex example, because here we have if and else. In this case, what we do is, again, we have to compare, in this case, A and B. To get the mask, we first operate on the if, on the body of the if statement. In this case, we store elements from A to C, and then we complement the mask, and finally we perform this second store from B to C. Notice that first of all, when we create in this if statement, or in this comparison here, we create the vector mask, we will have that, for example, A0 is smaller than V0. So in this case, we have the vector mask is 0. So what that means is that for element 0, we are not performing this operation. We will perform this operation, but we do that later after we complement this mask and all the zeros become 1 and all the ones become 0, in order to be, or before executing step 4. Okay, there are some issues with the stride unbanking, as we are going to discuss, because if we want to have, let's say, the perfect access to the bank memory and the maximum throughput or the maximum bandwidth of one element per cycle, we need to have a stride and number of banks to be prime relative. And what that means is that they don't have common multiples, because if they have common multiples, then we will have bank conflicts. Remember that the ways that we can store a matrix in memory is row major or column major. In row major, consecutive elements in a row are laid out consecutive in memory. In column major, consecutive elements in a column are laid out consecutively in memory. So, and we may need to change the stride depending on how the matrices are stored. In our matrix multiplication example, remember that matrix A was accessed with a stride equal 1, while matrix B was accessed with a stride equal 10. So in this case, we have different strides, and the fact that some of these strides might not be a prime relative to the number of banks, for example, 16, these may cause bank conflicts. But how do we minimize them? We are going to see some ways of minimizing them, but first of all, let's make sure that we understand what we mean by a bank conflict. Imagine that we have to access element 0, element 2, element 4, element 6, element 8. We are only accessing the even number elements of one array. And because this array has a number of elements, and the size of these words is the size that we can fit in each of these banks, we will typically have element 0 of the array here in bank 0, element 1 of array of the array in bank 1, element 2 of the array in bank 2, and so on. In this particular case, we only want to access elements that reside in even banks, because we only want to access elements that are even numbered. So we would access here an element 0, we would access here element 2, element 4, and so on, until here in bank 15 we won't have any access because this is odd numbered. So the access to element 16 will be here to bank 0 again, because element 16 is going to reside here in bank 0 because we only have 16 banks. So what that means is that we cannot start the access to element 16 until we are done with the access to element 0, unless we have more than one load port. But if we assume this kind of configuration with a single load port, with a single MDR and a single MAR, we will have to wait for the access to element 0 to get complete before we go to the access to element 16. And that is what means bank conflict, and that reduces the throughput or the bandwidth of our memory. How can we minimize bank conflicts? Well, the very first idea we could have is to add more banks. Is the most straightforward idea. In the previous example, if instead of having 16 banks, we have 32 banks, then we don't need to wait for access to element 0 to be completed in order to start the access to element 16. But that's the most straightforward solution. Another solution is to add more ports in each bank, as we have mentioned before. And in that case, we could sustain, for example, if we have 2 load ports, we could sustain 2 accesses simultaneously to the same bank. Or we can have a better data layout to match the access pattern. For example, one way of avoiding bank conflicts when we have to access matrix B in the matrix multiplication example would be to transpose matrix B such that columns of matrix B are placed, or elements in the same column of matrix B are placed in consecutive memory locations in their linear memory, right? However, doing this might not always be possible, not for workloads. And also, of course, it might entail some overheads if we really need to do the transposition. Another possibility is to propose a better mapping of address to bank. Notice that in our examples until now, we have just considered the idea of having a linear mapping of address to bank. Address 0 goes to bank 0, address 1 goes to bank 1, address 2 goes to bank 2, and so on. But it's possible to have kind of randomized mappings, have been proposed multiple times in the past. This randomized mapping can avoid bank conflicts because it makes more difficult for two accesses with the same stride or with a certain stride to fall in the same memory bank. A very good example of this works is this paper by Bob Rao presented in MISCA 1991. And this is the abstract and the beginning of the paper. Okay, we have covered, let's say, the basics of SIMD processors, vector and array processors. Now we are going to continue talking about SIMD operations and SIMD processing in modern ISAs. We started with this example, or we briefly covered this example in our previous lecture. Now we are going to recap on it very briefly, and then we will continue talking about where in current existing devices that we are using every day, or we would be using every day, we can find this SIMD paradigm. Remember the example of MMX, the multimedia extensions in the x86 architecture the other day. We covered this example where we want to replace the blue background in an image X with a blossom background and generate a new image like this one on the right-hand side. So in order to do so, first thing is to generate a mask. As we have just seen in our previous example, we use this packed compare operation in order to obtain the mask. What we essentially do is for every single pixel, every single element of image X, we compare it to the value blue to see if the pixel belongs to the background or not. And based on that, we generate this bit mask. Then in the next instructions, we use this bit mask to filter those elements either from the blossom image or from the woman's image that we want to use in the final image. And then we merge the filter pixels using this packed OR instruction. So here you have at the bottom of the slide, you have the complete code, and you can find many more details and other examples in the original paper. So more recently, or in successive years, the SIMD extensions in the x86 architecture continued evolving. The very first generation was MMX that operated on integers and had registers of 64 bits. A few years later, the streaming SIMD extensions, SSE, appeared. They already featured registers of 128 bits, so they could hold twice the number of elements, either integer or single precision floating point. In SSE2, we have already double precision floating point operations, and in the later generations of SSE, the SSE3, the supplemental SSE3, and in SSE4, we have new instructions. In particular, I would highlight the shuffle operations in SSE4 that allow you to shuffle around bytes belonging to the same vector register. And also, well, we will talk about these kind of shuffle instructions in GPUs in a later lecture. After the SSE generation, the advanced vector extensions extended the size of the registers to 256 bits, also on floating point, and AVX2 floating point with fuse multiply add. It's an operation that executes a multiplication and an addition in the same cycle or in a single cycle. It's very much useful for important modern workloads like machine learning workloads, and AVX 512 that further extended the length of the vectors to 512 bits. And more recently, the advanced matrix extensions use two-dimensional registers to execute a tile multiply, matrix multiply operation with a tile multiply unit that is designed for AI and ML workloads. If you want to learn more about SIMD processing more in detail, the contents that we have quickly reviewed today, I can recommend you this lecture from Professor Mutlu from spring 2021. But we don't only find SIMD units or SIMD operations in the x86 architecture. We also find SIMD operations in modern accelerators, especially those targeted at machine learning. A very good example is the, Cerebrus wafer scale engine. It's the largest ML accelerator that essentially is not a single chip, it's like a whole die that the very first generation had 1.2 trillion transistors, and as you can see on the slide, much larger than the largest GPU of that time. In 2021, they released the second generation, the wafer scale engine 2, with essentially twice the number of transistors and cores, and again, much larger than the larger GPU in 2021, that is the A100 architecture from NVIDIA. And using this huge accelerator that can hold multiple layers of a neural network at the same time requires to figure out what's an optimum mapping of the network on the existing wafer scale engine. Imagine here, this is the wafer scale engine, and it has been divided in different parts. Different tiles of the wafer scale engine are being used to compute different layers of the network. So in the end, what we have here, we are executing different layers of the network in a MIMD machine, because we have multiple instruction streams from different neural network layers operating on multiple data elements at the same time. So in this Cerebrus wafer scale engine, we have MIMD execution, and we also have SIMD execution. Let's see it with a little bit more detail. Notice here on the right-hand side, we have the entire wafer scale engine. It's divided into tiles, into dies. If we check inside a single die, what we find is a bunch of tiles, in this case, more than 4,500 tiles. And inside each of these tiles, we have different elements that we are going to discuss in the next slide. But observe that these different dies and these different tiles are connected with a 2D mesh interconnection fabric to move data, to make the data flow over the neural networks being executed on the wafer scale engine. So this is a MIMD machine, but if we go deeper into the tiles, what we will find is a SIMD processor, and in particular, we can identify the fuse multiply add unit that can execute, or is essentially a four-way SIMD unit that executes this AXPI operation. We perform a multiplication and then one addition. We also have these address registers in order to address the access to the local memory, a local SRAM of 48 kilobytes, as you can see. So if you want to learn more about the Cerebrus wafer scale engine, I can recommend you this Safari Live seminar delivered by Sean Lee on February 28th. Okay, so we continue talking about heterogeneous computing systems. We have, refreshed what are the basic ideas of SIMD processing, vector and array processors. We have seen examples of SIMD processing in real processors like x86 processors or the Cerebrus wafer scale engine, but these are maybe not even the most popular form of SIMD processing these days. And probably one very good example are GPUs, and we are going to start talking about GPUs right now, and as you'll see also GPUs, because they are so representative of heterogeneous computing systems, or are, let's say, the most representative device and accelerator of heterogeneous computing these days. We are going to spend the next lectures on learning more about the architecture, the programming model, how to program, and how to optimize code for GPUs. But let's start talking about its architecture. Remember this figure from the previous lecture. It's the block diagram of the NVIDIA A100 as a state-of-the-art GPU that contains 108 GPU cores and 40 megabytes of L2 cache. It also has the current version of the A100, 10 memory controllers to access 5 stacks of HBM memory and achieve a memory bandwidth of 1.5 terabytes per second to this HBM memory. Total size of this HBM memory is 40 gigabytes. But if you see this block diagram, it clearly appears to be very complex, but in reality, it's not that different from what we have seen in the beginning of these lectures, array processors and vector processors. Remember that in array processors, we have multiple processing elements that are able to execute different operations, while in vector processors, we have multiple processing elements that each of them is specialized on a different operation, like a load or an add. If we look closer at the core of the GPU A100, we will see something similar to vector and array processors. Notice how we have different execution units here. Some of them are specialized for integer 32-bit computation, or single precision floating point, or double precision floating point. So these are different units specialized for different instructions, but at the same time, we have multiple of each of them, similar to what we have in an array processor. In this particular case, or in this particular part of the figure, what we have is 16 32-bit integer ALUs, right? And these are also pipeline. Or we also have these tensor cores here that are also a different type of execution unit. And as we will see at the end of this lecture, they are also SIMD units as well. But there is something more that resembles in this core what we have seen in the slides from the beginning of this lecture. It's that we also have bank memories in GPUs. And in particular, this shared memory that you can see here at the bottom of the A100 core is a bank memory. And we will talk about it in detail and about how to access this bank memory in a later lecture. So GPUs are SIMD engines underneath. The instruction pipeline operates like a SIMD pipeline, so it's similar to an array processor, also a vector processor. However, programming is done using thread, not instructions. In previous slides or in the beginning of the lecture, we have seen vectorized code using vector instructions. In this case, or when programming GPUs, we are not going to use SIMD instructions, we use threads. In order to understand this better, we will go back to the simple example, the parallelizable or vectorizable for loop. But before that, it's important to distinguish between what we call the programming model that refers to the software and the execution model that refers to the hardware. It's important to distinguish between these two in order to understand the way that we program different systems and in order to understand the way that the instructions execute on different devices. So the programming model refers to how the programmer expresses the code, and this can be done in a sequential way. For example, if you just write code in plain C, or in a data parallel manner, for example, if you use SIMD instructions, or in a data flow, or in a multi-threaded manner. while the execution model refers to how the hardware executes the code underneath. And this can be in an out-of-order execution, for example, an out-of-order processor, or a vector processor, or an array processor, or other types of processors. So the execution model can be very different from the programming model. For example, we can write a sequential C code using the von Neumann model, and then execute this sequential code on an out-of-order processor that will be able to extract some instruction level parallelism. We are going to see an example next. Or we can use a multi-threaded programming model, for example, SPMD, single program multiple data, and execute it on a SIMD processor. And this is actually the model that we follow in both programming model and execution model that we follow in GPUs. We are going to see how. So remember our simple code, simple for loop, where we just execute one vector addition. We are performing the element-wise addition of elements from A and B. And if we write this using sequential code, what we will do is something like this. We will first write one load instruction or one load operation, then another load operation, then one addition, and finally a store operation. And this is going to be repeated multiple times, as many as iterations has the for loop. So we can execute this on a sequential machine because it's a sequential code, but it's also possible to extract some instruction level parallelism. And we can extract this instruction level parallelism because the iterations are independent, as we will see. And because even within each iteration, there are operations that are independent. For example, these two loads are independent and could be executed eventually in parallel. So let's take a look at how we could execute this code on different execution models. For a programming model, the most naive programming model, sequential, these can be executed on a pipeline processor. In the pipeline processor, like a MIPS processor, what we have is a pipeline. In every single cycle, we issue one new instruction. So first of all, we would issue this load, then this other load, and then whenever possible, this add. Probably we'll have to stall the pipeline for a while if we don't have a data forwarding unit. But in the end, we will execute here instruction by instruction in order. Or we can execute this on an out-of-order execution processor, like an Intel CPU. And our out-of-order execution processor is going to be able to execute those instructions that are independent of each other. For example, these two loads. So multiple iterations can run in parallel as well because they are independent in this out-of-order processor. So in some sense, the loop is being dynamically enrolled by the hardware. And also, we could execute this code on a superscalar or a very long instruction word processor. Why is that? Because in the end, there is also instruction level parallelism that we can extract from the code, and we could execute multiple instructions per cycle, right? Again, here, these two loads are independent, or this add is independent of this add. So we can take advantage in a superscalar or a VLIW processor. Now, we can also execute these, or we can also write the code in a data parallel fashion using a SIMD programming model, but we can also execute this in parallel, right? So the realization here is that these each iteration in the for loop is independent. So this iteration 1 can be executed at the same time as this iteration 2, and so on. Now, the idea is to have the programmer or the compiler generating SIMD instructions to execute the same instructions from all iterations across different data. So we can create a SIMD instruction, for example, with these all these loads, remember, from array A. So this would be a vector instruction, and in our vectorized code, we would write something like this. And then we have another another load that we can vectorize. So this would be the next vector instruction of our vectorized code. And then we have the addition, and then we have the store operation. So these can be for sure executed on a SIMD processor, a vector or array processor, as we have seen before. But the point here is that we can also write the code in a different way. We can use multiple threads instead of using SIMD instructions. Again, the realization is that each iteration is independent, so we can assign each of these iterations to different threads. So now, instead of creating or writing a code where we use vector instructions or SIMD instructions, we are going to use scalar instructions. We are going to use individual threads to operate on the different iterations. And this could be executed on a MIMD machine, for example, a multi-core CPU or a multi-thread CPU. This particular model is called single program multiple data, but this could also be executed on a SIMD machine. Why is that? Because we can, as we will see, we can convert these threads that are let's say, programmed independently. We could turn them into SIMD instructions, because in the end, the way that we are creating the parallelism in our code matches to the same thing. So this could be executed on a SIMD machine, and actually, if executed on a SIMD machine, we call it single instruction multiple thread, and this is the model that GPUs follow. So a GPU is a SIMD or a SIMD machine. The main difference with a SIMD machine is that we don't use SIMD instructions to program. Instead, what we use are threads, and that's why we say that we are using the single program multiple data programming model. So each thread executes the same code, but operates on a different piece of data. And we can assume that each thread is going to have its own context. After writing the code, it will be the responsibility of the hardware to generate the SIMD instructions from the code that we have written for threads. So the hardware is going to group the threads into something that we are going to call warps for NVIDIA architectures, or waveform in AMD architectures. And these warps or waveforms are essentially SIMD instructions or sequences of SIMD instructions. So a warp is essentially a SIMD operation or a string of SIMD operations formed by the hardware. A warp is a set of threads that execute the same instruction. So same as we could in our previous programming model, in the SIMD programming model, we said that these two loads and the rest of loads could go to the same vector instruction. Here, we can group these loads into warps or into instructions for different warps. So this would be instruction load for warp 0, this instruction load, next instruction load for warp 0, and add for warp 0, and a store. So graphics processing units are SIMD processors not exposed to the program. That's why we call them SIMT. Main differences, to summarize, as in SIMD, we have a single sequential instruction stream of SIMD instructions, and we use vector instructions and vector registers and a vector length register and a vector mask register, while in SIMD we have multiple instruction streams of scalar instructions. We have multiple threads, and the hardware groups the threads into warps. So from the software perspective, we have a number of threads, and we have scalar instructions like loads, adds, stores, and so on. SIMT has two major advantages over SIMD. First of all, that each thread can be treated separately, and this gives us the possibility of writing code as if we were writing code for a MIMD machine, for a multi-core CPU. And also, it's possible to group the threads into warps in a flexible manner, and in order to maximize the benefits of SIMD processing. So let's first talk about the first advantage. Remember that what the hardware is going to do is taking the code written for threads and generating warps. And how are these warps going to be executed on the hardware? They are going to be executed in a multi-thread manner. So what that means is that warps are going to be, or the execution of warps is going to be interleaved onto the pipeline of the execution units. We are going to assume that a warp consists of 32 threads because that's the typical number in NVIDIA architectures, and the waveforms in AMD architectures typically have 64 threads. So if our warp size is 32, and if we have, let's say, 32,000 iterations, we will, and we assign 1 iteration per thread, we will need 1,000 warps. And now these warps, or the instruction streams of these warps, are going to be executed on the same pipeline in an interleaved manner. And this is what we call the fine-grained multithreading of threads. So in the, let's say, initial cycle, we can start, for example, this instruction for warp 0, and then this instruction for warp 1, and then this instruction for warp 20, because the previous 2 instructions for warp 20 have already been executed, and so on. Very briefly, remind you what is fine-grained multithreading. Essentially, fine-grained multithreading is a technique that consists of having multiple hardware contexts in CPUs. Each of these hardware contexts corresponds to one individual thread or hardware thread of the CPU. In GPUs, when we talk about hardware context, we mean the hardware context of one warp, because all threads that belong to the same warp use the same program counter. So by thread context or by warp context, we refer to the program counter of this warp and the registers assigned to this warp, including mask registers. So the key idea in fine-grained multithreading is that we have these multiple hardware contexts, and every cycle we fetch instructions from a different thread. And the advantage of doing that is that we don't need to worry about handling control and data dependencies within a thread. We don't need to stall the pipeline until one particular instruction of the same thread has been completed, because after issuing one instruction from one thread, we start fetching and issuing instructions from other threads. So this way we hide all the dependencies, and we can also hide the latency of long latency operations, like, for example, memory accesses. So we switch to another thread every cycle such that no 2 instructions from a thread are in the pipeline concurrently. So as I said before, this allows us to tolerate long latencies due to, for example, control or data dependence, or long latency operations like memory accesses. If you want to recap and learn more about fine-grained multithreading, I can recommend you this lecture from Professor Mugdu, or these other lectures from previous editions of the course. So this fine-grained multithreading technique also applies to the warps and the execution of warp instructions on the SIMD pipeline of GPUs. So for every single warp, we have the warp is composed by multiple threads, and they have a common PC. So here you have another view of the GPU. This would be this shader core, would be what we normally call a GPU core. It's also called a streaming multiprocessor in NVIDIA terminology. And if you look inside this shader core, what we find is multiple of these hardware contexts with PC, with mask, for the different warps. And then we have here instruction cache, a decode stage, and then we have the execution unit that is composed by multiple scalar pipelines where we execute the instructions for the different elements being operated by the different threads that belong to the warps. And here you have another view of this shader core, or this GPU core streaming multiprocessor. We can see in this part of the slide how we have different warps or different instructions from different warps ready for the execution at some point. For example, here at this point, we are issuing one instruction from warp 7 into the SIMD pipeline. Here you can easily recognize the fetch stage, decode, access to the register file, access or execution in the ALUs, and eventually access to the cache or the shared memory that is also on chip inside the GPU core. Eventually, either the shared memory or the cache will miss, so we have to go to the lower levels of the memory hierarchy, L2 or the global, the memory, the external off-chip DRAM. So while we are performing these operations, it's possible to continue the execution in this pipeline of instructions from other warps, and this way tolerate these long latency operations. And here you can see a more simplified example of how to execute, for example, an addition for a 32-thread warp. If we have a single execution unit, a single scalar unit, we will need to pipeline the execution of the addition for the 32 threads. So, for example, here in this cycle here of the pipeline, we are finishing the computation of addition A0 plus B0, and here we have addition A1 plus B1, and here the next element, and so on. And every single cycle we start the addition for 2 more elements coming from A or B. And this is the case where we have a single functional unit. It's pipeline, so we are exploiting the concurrency. In time, we may eventually have more complex, more powerful hardware where we have, and as is actually the case in NVIDIA GPUs, we have multiple of these functional units, and we can execute multiple of these instructions, operations at the same time. So we are exploiting concurrency in time and in space. And if we look at the structure of these functional units, we are going to have several of these execution units forming a SIMD functional unit that execute all of these ALUs here, the same instruction. And we can have also other units for other operations. And we will also have a certain number of registers that are assigned to the threads that execute in these execution units here. So all these execution units that have access to the same registers and the registers themselves assigned to each thread is what we call a lane. And here we have another example. In this particular case, we assume that we have 32 threads per warp, but we only have 8 lanes. And what that means is that every single cycle, we can start the execution of an instruction, for example, a load instruction in the load unit for 8 of the threads of the 32 threads. And in the next cycle, we will start the execution of the next 8 threads and so on. And after 4 cycles, we would have issued the whole load for the 32 threads of the warp. And we can do the same in a multiply unit or in an add unit, and then for later instructions coming from different warps. But now the point is, if I'm going to program these warps by using threads, and I'm going to have a single program, because I'm using the single program multiple data programming model, how should I refer to the data elements that we have to access from memory and we have to operate on? And to do so, what we do is using the thread ID. Here, you have a nice figure here showing how we assign threads from 0 to 15 to data elements in one array, this green array here, such that when we divide the computation or group the threads into warps, we have the threads in the different warps operating on the corresponding element. But how do we express this in code? As I said, we have to use the thread ID. So in our CPU code, we will have only a single for loop like this and sequential execution of these instructions of these iterations here, while in the CUDA code, by the way, the name of the CUDA functions is kernel, and it's typically identified by this global qualifier, as we are going to see in the next lecture. If you look at the body of this kernel, the first thing that we see is the thread index that identifies the specific thread that we are writing this code for. And the value of this thread index is going to go from 0 to the maximum number of threads that we are using in our program -1, as you can imagine. And after that, we perform the accesses to the arrays in memory and the operations and final store back to memory again using the thread ID. So how are we going to execute these kernels on the GPU? Is this the only thing that we are going to have in our programs? I don't think so, because all codes will continue having some parts that are sequential or modestly parallel. I mean, all say complete applications, but we will execute those parts of the computation that are massively parallel on the GPU. And the way of writing our code is going to be using blocks of threads. It's not just like writing the code for a thread and then assuming that we are going to launch thousands or millions of threads, but also that we can group the threads into some software construct that we call block, and later these blocks are going to be assigned to the GPU cores and executed, forming warps, as we will see. But the typical structure of a program is going to be CPU threads executing serial or modestly parallel code. At some point, we will launch the execution of the kernel on the GPU. As I just said, we are going to define a number of thread blocks or blocks of threads and a number of threads per block. So the, let's say, arrangement of threads is going to look like this, as you see in the slide. At some point, the kernel will terminate, and then we continue the execution on the host CPU, and then we again launch a new kernel, in this case, kernel B. We will get more familiar with the syntax of the kernel launch in the next lecture. The execution or the advantage that we can take of a heterogeneous system with a parallel processor like a GPU is attached to the Amdahl's law. As you may remember, Amdahl's law determines or defines what's the maximum theoretical speedup that we can get from a system with a number of processors n. In the end, the maximum speedup that we can get is limited by the serial portion, that is this 1 minus f that we have here. And that's also something to take into account when we are executing heterogeneous programs on heterogeneous systems with, in this case, CPUs and GPUs. And continuing with the execution of threads on the GPU hardware, I was just saying that when we write our program, we organize our threads in thread blocks or blocks of threads. When these blocks go to the hardware and have to be executed on the GPU core on the streaming multiprocessor, here we have an example, streaming multiprocessors from the old NVIDIA Fermi architecture. These blocks are assigned complete blocks to the cores, and inside the cores, these blocks are decomposed into warps of 32 threads. Typical, so for this reason, the typical size of a block is going to be a multiple of 32. So if these block 0 or this block 1 or 2, for example, they have a total of 128 blocks, and that means that they have 4 warps, or they will be decomposed into 4 warps when executed on the GPU core. So in order to recap and summarize this comparison between warp-based SIMD and traditional SIMD, in traditional SIMD, we have a single thread, and this thread executes sequential instructions, but these instructions are SIMD instructions. So the programming model is SIMD. There is no extra threads. What we are just doing is using vector instructions or SIMD instructions in general. In warp-based SIMD, we write code for scalar threads, and these threads are going to be executed in a lockstep manner on a SIMD machine and on the SIMD pipeline. Because in the end, what the hardware is doing is grouping the threads into warps, and these warps behave, or the instructions for these warps behave as SIMD instructions. The good thing is by using the single program multiple data programming model, we can treat each thread individually, and this allows us or gives us the opportunity of having threads diverging and not necessarily going all of them over the same path. Of course, as we will see in later lectures, it's going to be better when we reduce or we minimize the divergence between threads that belong to the same warp. Why is that? Because the hardware will be better used and the execution will be more productive. We will achieve higher throughput, computing throughput, when we take advantage of the whole warp and use all available execution units. But if it's needed, and because we are using a scalar ASA, it's possible to make threads diverge. And in order to support that, the SIMD hardware has vector masks, as we know. So in the single program multiple data programming model, it's a programming model rather than a computer organization. Each processing element executes the same procedure except on different data elements. These procedures can synchronize at certain points. We have barriers, and we will see how to use barriers. We will start talking about them in the next lecture. But essentially, we have multiple instruction streams executing the same program. Each program or each thread or each procedure, I prefer to call it thread, works on a different data and can execute different control paths, as I mentioned before. So this facilitates programming because it gives programmers the impression that the code is going to be executed on a MIMD machine, even though it's going to be executed on SIMD hardware. Remember as well that we talk about the possibility of grouping warps flexibly, and this relates to the way that conditional control flow instructions are being executed. For example, we can have different paths for different threads, like this thread 1, 2, 3, and 4. So they can diverge, even though they may, or they have to, or they may belong to the same warp, and they have a common PC. How are we going to execute this? How are we going to solve the control flow problem on a GPU? How we handle this branch divergence? We simply have in each path of a branch those threads that have to execute that path of the branch. And here you see like different, like one warp going over different instructions. At some point, path A, only half of the threads are active, and then in part B, only part of the threads are active, and then at some point they will reconverge. But in this part where we have branch divergence, we can use the conditional or predicated or mask execution and the the vector mask registers. Okay, so we have more or less given an introduction of the architecture of SIMD processors and GPUs. We have seen in the very few years, let's say 12, 15 years, how the GPUs have evolved at a very fast pace, and essentially the number of functional units and the number of the throughput in gigaflops has increased by an order of magnitude since the G80, also called Tesla architecture, back from 2006, 2007. Even this GTX 285 from 2009 also belongs to that G80 architecture. After that, we had successive architectures: Fermi, Maxwell, Pascal, Volta, Turing, and the most recent Ampere. And you see somehow the evolution of these GPUs over the years in this plot. We will talk about specific features of the GPU architecture that have been incorporated over time, over these 12 to 15 years, and how the architecture has evolved, and this has enabled many things that could be done by programmers and facilitate programming, and also increase the performance and energy efficiency of the GPU programs. At the end of the course, hopefully you will understand very well the architecture of this NVIDIA A100 GPU, and also how to program and optimize code for it. And we will talk in more detail about the GPU course as well. The only thing that I would like to show just before finishing is a little bit of the microarchitecture of these Tensor cores that were introduced in the Volta architecture like 3-4 years ago. They are also, as we can see in this slide, are SIMD functional units, but they are a little bit special because they are designed for the execution of matrix multiplications. In particular, when executing instructions for different warps or for a warp, and this according to the paper that you can find at the bottom that did some micro benchmarking of the architecture in order to understand the internals of these tensor cores. Each warp utilizes 2 tensor cores, and inside each tensor core we have 2 octets, and each of these octets is composed by 8 of these SIMD units, as you can see here, that execute dot product operations. Here you can identify multipliers and a tree of others to perform the dot product operation. A 4x4 matrix multiply and accumulate can be executed in each cycle per tensor core. In the end, as I said, this looks a lot like a SIMD unit, but one interesting characteristic of these SIMD units, of these tensor cores, is that unlike conventional SIMD units, the register contents are not private to each thread, but are shared across all the threads inside the same warp. And this is important to execute the matrix multiply operation and not having to replicate elements of the 4x4 matrix, which in the end is just like a submatrix of a whole, a larger matrix multiplication, not having to duplicate or replicate some of these elements to be accessed by different warps. Sorry, by different threads of the same warp. That's a good thing of having these shared registers within a warp. In order to finalize the lecture, if you want to learn more about the architecture and all the different things that I have covered about the architecture of graphic processing units and the programming model, I can recommend you this longer lecture from the Digital Design Computer Architecture course from the past spring 2021 semester. And also you have a longer version of this lecture on SIMD processing and GPUs in the computer architecture course from the past fall 2021 semester. This is all from my side. Feel free to reach out to me if you have any questions or you want to discuss anything related to this lecture or the course in general. The only last thing that you can find as a backup slide in this presentation is this final slide with some clarification about some GPU terms in the generic terminology, NVIDIA terminology, and AMD terminology that I think can be useful to clarify a little bit more at this lecture. Thank you very much for your attention, and